Good morning everyone. So today we are going to look at the second mechanism, which is known as dehydration of alcohol. It is a type of reaction for elimination reaction. So elimination means that you want to remove something. And from dehydration, it means that you want to remove water molecule. When you remove water molecule from alcohol, it will become an alkene. Generally, take this as an example. When this ethanol, it undergoes dehydration with the reagent concentrated H2SO4 under condition heat, it will form ethene and a double bond is formed. So you need to know about what is the step to remove water molecule. We will first remove OH first, followed by H. We'll remove the most awkward one, which is the nucleophile, followed by electrophile, which is the most common one. Another thing that you need to know is about Say-Zapp's rule. Say-Zapp's rule can only be applied when you have at least 4 carbon, and it needs to be applied when you have carbocation. And from the word Say-Zapp's, it means that more alkyl will be more stable. So let's have an example. Let's say for this one. When you have carbocation, you need to consider about Say-Zapp's rule. However, from Say-Zapp's rule, we know that when you have more alkyl, you become more stable. So when you see here, there are 2 types of carbon that is adjacent to carbocation here. So one is at the right hand side and is at the left hand side. You can see that at the right hand side, this is a secondary carbon, but this one is a primary carbon. So it means that this C will be our target because it has more alkyl. It is attached to more C. So when you have carbocation and you want to form double bond, we will choose the right hand side to be the major product, which is this one. And for the left hand side, it will become a minor product. And normally in exam, for mechanism, you just have to draw out the major product, no need the minor product. Say-Zapp's rule cannot be applied if the carbon is less than 4. Let's say for this as an example. For this one, it is with 3 carbons only. So if you apply Say-Zapp's rule, the left hand side and the right hand side will be the same carbon, which is primary carbon. So this means that Say-Zapp's rule cannot be applied, because when you put at the left hand side the double bond or the right hand side the double bond, it is basically the same. It is just the reverse of the compound. So there is actually no meaning if you apply Say-Zapp's rule, because there's no major or minor product. So let's have a look at the first example. Given this compound, when it reacts with concentrated H2SO4 under the heat, what will it form? Remember, just now our main objective for dehydration of alcohol is to remove OH, followed by removing H, and then lastly, when you have carbocation, you need to form double bond to form alkene. So I will write the aim here. But this is not the step for the mechanism. This is just a guideline for you to refer to. So let's see at the first step of this mechanism. We know that concentrated H2SO4 is an acid. So when it dissolves in water, it will form H3O+, which indicates the presence of acid. So in the first step, this compound will react with H3O+, which is this one. Okay, and then You need to remember that for every step for dehydration of alcohol, you just have to consider from unstable, you become stable. Unstable means that it has a positive charge. Let's say for this case, it is H3O+. It is not the H2O that we normally learn, so it is unstable. To make it become stable, we want to get back what we have before in order to make it become H2O. So the first step, H3O+, the bond between O and H will break and the electron will go to O in order to form back H2O. So the remaining H will be taken by this O, which is highly electronegative. It will get the H in order to help the H. So it will become this structure. But the story is not end yet, because we didn't even remove OH for the first step. So remember, it is still unstable because there is positive charge. So you need to break the bond between C and O, and the electron will go to O in order to form again H2O. And this will also lead to the formation of carbocation here, and then this compound. And from this second step, we know that OH is already removed, because here is already removed. So our first step is achieved. So we take at the aim for the first step, remove OH, we have done. So next step, we will need to remove H. And we know that if we have carbocation, we must remember about Say-Zapp's rule to form double bond. Say-Zapp's rule can only be applied when there is carbocation. Okay? So this one is still positive. It still need to undergo the reaction again with the help of H2O. H2O comes from here. Okay? So we need to remove H in order to form double bond. So this H2O, the oxygen, highly electronegative oxygen, will get this H, and the bond between C and H will break in order to make this bond over here to remove the plus symbol. And the final product will form this structure together with H3O+. So the second aim, which is to remove H, this step is shown by this one, remove H, and then third one is the formation of double bond. So once all the steps are completed, all the aim are achieved, this means that the mechanism is ended. Next, the product form will be this, which is this one, together with H2O. And in mechanism, we only care about the major product after we applying for the Say-Zapp's rule. And the minor product normally we will not consider for mechanism. A note that you must take note is that for the third step, when H2O attack H, it cannot attack this H, because if you see here, if this oxygen, highly electronegative oxygen, attack this H, what it will occur is that C and H, the bond between them will break and the bond goes over here to remove plus, right? However, this also means that there is no 4 bonds already over this C. So this doesn't make sense, and it is not correct, because carbon, we will have 4 bonds in order to become stable. Next, we will look at the second example. Given this structure is reacted with concentrated H2SO4 under the condition heat, what will we form? So the same aim, we will need to remove OH first, followed by H, and then we form double bond. First, concentrated H2SO4 dissolves in water to form H3O+, and then H3O+, the original version is H2O, right? So we need to make it to become stable as before. So the bond between O and H will break in order to make this H3O+ become H2O. And then the remaining H will be taken by this highly electronegative oxygen, which is partially negative, will attack partially positive atom to form this structure. But the story doesn't end yet, because this is still positive, it is unstable, and we didn't even remove OH. So we will remove these unstable ones by breaking the bond between C and O to form H2O back. Next, this structure will be formed because the bond between C and O breaks and a carbocation ion is formed. And when you see carbocation ion, you must also remember, before you do Cesar's rule, you must also apply another thing called 1,2 hydride shift, or sometimes 1,2 methyl shift. What are them actually? So let's have a look at these two shifts. There are two shifts that may occur when you have carbocation ion. One is 1,2 methyl shift and one is 1,2 hydride shift. Methyl is CH3, which is originally from CH4, methane. When methane becomes a substituent, it is called as methyl. Another one is called as 1,2 hydride shift. Hydride is H. Both of these shifts may occur when you have carbocation ion. In other words, when you have carbocation ion, you must consider rearrangement by either having 1,2 methyl shift or 1,2 hydride shift. The reason why we need these two shifts is because when we have a less stable carbocation ion, we want it to become a more stable carbocation ion. Because if the carbocation ion is more stable, it will make the reaction to be faster. So, for the carbocation ion stability, the tertiary carbocation ion will be the most stable one, as followed by secondary carbocation ion, then primary carbocation ion, and lastly, methyl carbocation ion. Now, let us look at some examples. So first, when we see this compound, when you have carbocation ion already, you must consider whether you need to rearrange the carbocation ion or not. Because we need the more stable intermediate carbocation ion. For this case, rearrangement is needed because this one is a primary carbocation ion, but the carbon that is adjacent to the carbocation ion, which is this one, is more stable. It is tertiary. So you must consider rearrangement. When you see at the tertiary carbon, you may notice that it has 3 methyl groups that attach to it. There is no possibility to have 1,2 hydride shift to occur because there is no H that is directly attached to this C. But there are only methyl groups that attach to this C. So, to make the carbocation ion to be more stable, what it will do is that methyl group, which is attached to this C, happens to shift with this carbocation ion. And the resulting compound will form something like this. As you can see here, when the methyl group is shifted to here, this carbon has already achieved octet rule, so it does not have formal charge of positive 1. But this carbon will have a formal charge of positive 1 because it does not have 4 bonds that is attached to it. It does not complete octet rule. Another example is like this. When you have the carbocation here, you must consider about rearrangement if needed. For this case, it is needed because when you see at the adjacent carbon that is directly attached to the carbocation, you may see that this one is a primary carbon, but this one is a tertiary carbon, which means that this one can form a more stable carbocation. So what it will do is that there will be a 1,2 hydride shift to occur, whereby this hydrogen will go over here to form something like this. H is already shifted to here, but for this carbon, it will be with a formal charge of positive 1 because it does not have complete octet rule. So remember, 1,2 methyl shift or 1,2 hydride shift may occur when you have carbocation, and these shifts can only occur at adjacent carbon only. And the carbocation does not move, but it is H or CH3 that moves. Now, looking back at the example just now, when we have carbocation, and you see this one is only primary, we must consider rearrangement by looking at the adjacent carbon. And for this case, it only has one adjacent carbon, which is this one, and this attached to 3C. So this one is tertiary carbon with one H attached to it. So what it will do is that there will be a 1,2 hydride shift occur because this H has only one, but CH3 have two. So this one will be least. So this stingy neighbor will only give the least H to the carbocation just now, and then it will form this structure. After we consider rearrangement, then we will apply Say-Zapp's rule to form double bond. So these two compounds will go to react with each other. Oxygen, which is highly electronegative, will attack this H to remove H, and then when you remove this H, the bond will go over here in order to remove the positive charge to form this alkene and H3O+. This oxygen can only attack this H, but not the H here. Not attack the H out here, because if you attack this H, the product form is minor product, and for mechanism we only consider major product. Last example is this one. When this structure reacts with concentrated H2SO4 under heat, what will it form? Again, we need to apply the aim just now, which is first remove OH, second remove H, and third form double bond. When this one reacts with water, it forms H3O+. H3O+ is unstable. It will try to become H2O. By how? OH, the bond between them will break, and the electrons will go over this O to become H2O, which is a stable form. And then the remaining H will be taken by the partially negative oxygen, and it will form this structure. Next, we need to remove OH, right? So the second step will be this one. The bond between C and O will break, and electrons will go over this O in order to form H2O again, and the result will form carbocation over here. And remember, when you have carbocation, consider rearrangement if possible. So this case, rearrangement is needed because this is a primary only, but this one is tertiary. There will be a 1,2 methyl shift that occurs because there are only methyl over here, and then when the structure undergoes 1,2 methyl shift, it will form this structure. After you have carbocation ion, consider about Sayzab's rule, which you need to remove one H and then you form double bond. So this 1 and 2, these two structures will react with each other, and this partially negative oxygen will attack this H, which is partially positive, and the resulting will cause the bond between C and H break, and the bond will form over here to remove the carbocation ion. After the process, it will form this structure and H3O+. Once you have done all the aim, check back whether you have removed OH, H and double bond. If you have completed all the 3 aims, this means that your mechanism is completed. That's all for this video. Thank you.